Okay, and I just want to take you through a discussion of this part. So this case study is based upon Optus, the telecommunications company, and what you're asked to do is you're asked to write a report for executive management, and so I'll just read through this. It says, for this assessment, you're going to analyze some customer data for the telecommunications company Optus, and then write a report with your findings. So just a bit of background. So Optus is an Australian leader in integrated telecommunications, delivering cutting-edge communications, IT, and entertainment services. Your task. So Optus executive management would like you to do two things. Number one is to create a dashboard to demonstrate how they could better understand this data and use it to make business decisions. And the data we're talking about is in this spreadsheet here. So all you got to do for the first task is just build some dashboards to analyze trends and patterns that you can observe in the data. So I would encourage you to think about building pivot tables and that sort of thing. I'll take you through an example in a second. We'll just talk about the second question. Second question, or the second task, is to create a model to predict customer value, which is the total spend of the customer over the life of the contract. And they provided you with 3,000 rows of customer data collected over the previous year. And the data has the following structure. It's got these columns here. There's about a dozen or so columns, such as, let's have a look at the spreadsheet now. Such as, so here's the customer data. And as you can see, there's quite a bit of data. There's 3,000 rows of data. And we've just included a description of the columns, which is also here as well, same thing. So we've got call failure. It's the number of call failures. Complaints. So 0 means there was no customer complaint. 1 means they complained. So for instance, let's see. So these two customers here, or these three customers, had complaints for some reason. The subscription length in the total month as a number of total months. So for instance, this person here has been a subscriber for 37 months in total. The charge amount, it's an ordinal attribute, so 0 means lowest amount, 9 means highest amount. And so that's the what do you call it? When you recharge the card on your phone. Seconds of use, so pretty self-explanatory. Total seconds of calls. Total number of calls is frequency of use. Total number of text messages here for frequency of SMS. Distinct call numbers is the total number of distinct phone calls. Age group, the age of the customer, where 1 represents a younger age and 7 represents an older age. Tariff plan, 1 means pay as you go, 2 is contractual. Status, 1 is active, 2 is non-active. Age is the age of the customer, so age group, age. So this is how old they are in years. And customer value is the total calculated value of a customer, which is this one here. And then there's churn. Churn refers to, this is a business term. It refers to customers leaving. So 1 means that they're likely to leave, or the churn flag has been set on, and 0 means non-churn. There's a low risk of the customer leaving the service. And so let's think about this data. So let's think about task number 1. So create a dashboard to demonstrate how they could better use this data to make better business decisions. So I would just think about, what we're seeing here. So one simple thing you could think about doing is, for instance, running descriptive statistics. So if we go to, let's quickly add ins. So I think the first thing I'd encourage you to do is have a think about running descriptive statistics over here, just like we did many times before. We'll just select all of this all the way down to the bottom. Labels in first row and summary stats. And then we'll just expand this out. Okay, so this is good because it tells us something about the data. It tells us For example, for customer value, it tells us what the mean, the median, and the mode is. It tells us the standard deviation. It also tells us something about the skewness. So this looks like it's positively skewed. And the other thing you could do is you could do a dashboard. So you want to visualize the data as well. So one great way to do that is just to insert a pivot table. So we've done this previously as well. So we'll just, it says select table range. So it's automatically selecting everything, which is good. And yep, all good. So we can just click OK, and we get a pivot table in a brand new sheet. And we can think about, well, okay, well, let's analyze. So the important thing we want is customer value. So let's put that in values. And this says the total sum of customer value. Let's do something simple like just see customer value by subscription length. We could do customer value by age. And that's specific age. We could even do age group, might be even better, where 1 is very young and 7 is old. So here we have the total sum of customer value by age group. Okay, and we could even incorporate status here. So this is for active and inactive. Frequency of use. So you just want to think about what makes sense and analyze patterns. To visualize, you can just then go to insert and then pivot chart. And that just gives you a quick way to chart it. So just inserting this in here shows us a table with all of the age groups, for instance, all of the customer spend, the total sum of customer spend, and then a chart. Maybe you don't want to see the total, maybe you want to see the average. So we've done this previously, but if you go to values, you can change that over to the average. So this is the average spend over the lifetime of the contract for different age groups. So you can see that our most profitable age group is this is age group 7, which indicates like an older demographic. Second is the 20 or so age group. Looks like. So that's the sort of thing you want. So you want to come up with a number of different charts as a dashboard, and you want to make it look like nothing this fancy, but just come up with as many dashboards as you think is appropriate to analyze major trends and patterns that add value to the organization, and put them all together into a single dashboard. So to do that, let's just do another graph. Let's do let's insert a scatter plot. Go back to this sheet. So imagine we want to analyze, let's say, frequency of SMS and against, say, frequency of use, these two. So we might just want to select these two and just say, let's just do a scatter plot. So what are we looking at? So which one's which? Sort largest to smallest, 255. So I'd say that the frequency of use looks like it's the x-axis because it only goes up to 255. Largest to smallest, yeah. And frequency of SMS is the y-axis. Let's just label those. So let's go to chart design, add chart elements, axis titles. So this one here is frequency of use. And this one here is frequency of SMS. So I guess what we're seeing here is that you want to understand if there's any sort of trends and patterns, for instance. This is just another, like I'm not saying you should do this, but I'm just getting another visualization as an example. And so what we could do is we could right click on this and we could just cut it out. We could make ourselves another worksheet. Clicking on the plus, double click here, we'll just call this one dashboard. Make it a pretty color. Okay, move that to the start maybe. And we could just drop this in somewhere. And that other chart that we had, we'll cut this one out. And again, we'll just move this over here somewhere. Okay, and maybe you'll have like, half a dozen more to complete your dashboard, just major trends and patterns that you can observe. And that's what we mean by a dashboard for task number 1. So they want you to create a dashboard to demonstrate how they could better understand this data and use it to make business decisions. So I hope everyone feels okay with the first one. You're just building, maybe 6 to 10 different charts and putting them into that first dashboard tab that I created over here. And the second task is to create a model to predict customer value. Now, we're going to unpack this idea over the next couple of weeks. And so there's nothing really too much I want to say about that today, but we're going to start to talk about this from today, how you can actually forecast and predict what the customer value might be for a brand new customer. Now you're going to put all this into a report, and the report will be structured with the following sections. And I've got a sample report template to help you get to fast track you. So you can just download this Word document here, and you can just basically start to fill this in. I've already put in a cover page for you. Okay, so just fill in the details here. And then there's some placeholders and some headings for each of the sections that you'll be filling in, okay? All right, so we'll workshop this in the, we'll go through this in the tutorials this week. We'll help you sort of start the reporting process, and we'll open up this Word document and then start to fill in some of the details here and take you through how to fill this in. All right, so that's the report. Okay, so in this lesson, we're just going to go through what regression analysis is, and then at the end of this, we'll just do a brief high-level overview of what multiple linear regression is. So let's start off with this first idea. What is linear regression? Now, you've done this in school, I believe. So in school, you would have done something like a scatter plot, just like this, where you plot out a number of points along an X and Y, on an X and Y axis. And then you put this line in, which is called the line of best fit. And maybe you've come across this term before. I'll just add it here in the Zoom chat on the screen, maybe. So this idea of line of best fit is often what we teach in high schools and such. This is also known as a regression. So the technical term for it is actually a regression. Right, so these two terms are, synonymous. And what it really means is that you're drawing a line to summarize all of the data points that you're seeing in the scatter plot. And these regressions are quite useful because, number one, they show you the general trend, the way things are trending. And this trend could be linear, like you see here. Linear means a straight line, but it also could be non-linear. Like, for example, you might have a scatter plot that might look like this, and you might have some data points. Just drawing a few points here. So this might be a non-linear regression. Let's change the color. And so we might have something, if we drew a line of best fit, it might look like this. This is a non-linear regression. It still summarizes all the data points and it shows you a general trend or a pattern, but it's not a straight line. So here's a real-life example on the left-hand side, where we have, let's see, self-reported life satisfaction versus gross domestic product per capita. So GDP per capita, gross domestic product is like the total economic output of a country. All of the exports and all the value that they produce, that's the gross domestic product. Like for Australia, it could be, billions of dollars, whatever. And per capita, that means if you take that big number, the total economic output of a country, and you divide it by the population, that gives you the GDP per capita. So Australia, for example, in 2022, Australia's GDP was 1.325 trillion, and in 2022, Australia's population was this. So putting these two together, so, oops, what is, okay, so that would be AUD as well. Okay, so the GDP per capita is 33,558 US dollars per person, basically, is what that's saying. And then self-reported life satisfaction, there's a scale over here from 0 to 10, where 0 means that you're not happy at all, 10 means you're very happy. So where is Australia? I'm not sure. I'd imagine it's up here somewhere. It doesn't look like it's on here. Can't really see it. But you can definitely see that there's, like if you look at the countries down the bottom left, you can definitely see that these are countries that are developing countries, and these ones up the top here are the wealthy nations like Finland, Germany, United States, Israel, France, Japan, Singapore. So it seems like there's some kind of pattern, doesn't it? It seems like there's some kind of trend that the richer the country is, the more satisfied people are. And that makes kind of sense because I guess you've got more agency. If you're in a rich country, you've got more opportunities. And therefore that might probably looks like it equates to general satisfaction. Whereas down here, you've got less individual opportunities to make a life for yourself. So things are very tough, and so satisfaction is generally low here. But if we drew a regression line, it might look something like this. You might see a general pattern going this way. Now, some other points that I want to make is that you could use a regression to predict. So for example, if we had this regression here, and then what we could do is we could then, and I've discussed this previously, let's get a different color. If we knew the GDP per capita, we could probably predict, and there was an unknown country, but we know that the GDP is here, okay? Let's say here. We could simply just draw a line, and where it meets the regression, just bring it across, and we could predict what the satisfaction level might be given a particular, value here, for example. So what I'm saying is we can use regressions for predictive analytics. Two more important points. So the x-axis is usually where we put the independent variables, and the dependent variables usually go on the y-axis. What's an independent variable? What's a dependent variable? So think of, A affects or causes B. This idea that we spoke about last week with causality. A causes B. So we think of A as the independent variable. So this is the independent variable. I'm not going to write the full thing. Hang on, let me just use text. So A is the independent variable, and B is the dependent variable, because B depends upon A, or B is impacted, influenced, or affected by A. But A, like for example, I guess we could say that your GPA, right? Your GPA is the dependent variable, and the number of hours that you spend studying is the independent variable. Okay, so your GDP is impacted or affected by the number of hours that you study. Give me a shout out in the chat if all of this is making sense, what I'm saying. Just give me a thumbs up emoji, we appreciate it, just so I know that I'm on track. Jennifer, Jesse, Janyu, you guys okay? Just give me a thumbs up if all of this is making sense. Okay, thank you. All right, Jennifer, you okay? Janyu? Let me know if you have any questions. Okay, so let's move on to the second point. The second point that I want to make is in the next slide. Let's go to the next slide here. I'll just clear all this ink out. Okay. So what we've done here, that the same sort of chart that we've got here on the left, what we've just done is just got a scatter plot. It's the same axes, GDP per capita and happiness. Looks like happiness is measured on this psychological framework. I think it's called the Cantril ladder, whatever that is. I don't know what that is, but there's some kind of framework they use for the survey to measure satisfaction or happiness. In the example to the left, GDP per capita is the independent variable. Like I said, we put that on the x-axis, and happiness is the dependent variable. So we put that on the y-axis. So like I said, we can draw this regression line. As you can see, it's not very clear, but there's this regression line here in this color, and then we can, given a certain independent variable, we can predict what the dependent variable is over here and predict this. Okay, so how do you do this in Excel? Good question. So I've got a data. I think I put a data set here somewhere. Oh, no, I didn't. Let's use the one for the tutorial. All right, so we've got some data here we can look at. So let's say we've got, let's say we wanted to look at ideas and satisfaction. and see if there's some kind of, look at what that does in a scatter plot. Let's do that again. Ideas and satisfaction. We'll go to insert, scatter plot. Okay, so we have something like this. So we have this trend here. So what we can do in Excel is we can get Excel to draw a trend line or a line of best fit. We can actually get Excel to do the regression. And to do that, all we do is just select the data points, and then we can just right click on the selection and then go to add trend line. And it brings up this panel and it tells us like, okay, the default is a linear regression, which is a straight line. But as I said before, it doesn't have to be a straight line. You can have patterns that look different. It doesn't have to be a straight line. And there's different options here. Let's just do linear. And we'll also put on here the display equation on chart and display R squared value on chart. Cool, and we can close this panel. Let's go full screen. I'll just move this to a new sheet, so it's a little bit bigger. And here's the equation on the chart. Let's move that over here. Just make that a bit bigger. Yeah, so if you look at this equation, just ignore the R squared value. What I will say about R squared is that this is the square of the error, and the closer this number is to 1, the better that this line summarizes all of the data. Like if all of the data points, let's imagine if all the data points were on this line, just ignore the blue dots and imagine for example, that all of the data points were kind of like, I just need a circle. I don't have a circle. I've got a love heart. Let's do this. So imagine that all the data points are along this line here. I don't have a circle, sorry, I just got these love hearts. But imagine that these are all the data points. In that case, the R squared value would be 1. It would be sort of a perfect alignment, that this line would perfectly summarize all of the data points. If this is a 0, that means that it's everywhere. It's like this. If it's like close to 0, that means the line does a really bad job at summarizing the data points. That's what R squared means. But this one here, I want to draw your attention to, y equals something times x plus something else. And you recognize this from high school, hopefully. You might remember from high school this equation, y equals mx plus b. Does anybody remember this from school? Maybe you use different letters, maybe you use C or something like that. Does that sound familiar from school? This is like, what do they call it? Gradients, rise over run. You guys remember this from high school? Well, if you don't, this is the equation of a line on a 2D plane, where y is just, the y-axis. So y is the y value. M is the gradient, rise over run, and B is the y-intercept. I forgot to say x. X is the x value. So let's put this on the screen here for you. So I'd imagine you would have done this in like grade 7 or grade 8 in high school. Maybe it's been a long time. So yeah, the m value tells you the slope, like how steep it is, I guess, or how flat it is. The x value is just along the x-axis here. The y value is along the y-axis, and the b B value is the y-intercept. So if you were to extrapolate or stretch out the this line here, you would stretch it all the way out and just keep going. It intercepts at around about this value here. This is the y-intercept here. This is exactly where it crosses over the y-axis at 1.0531. And if you look at the scale, that's pretty good. Like my line is not great, but you can see that it's telling you that it's about here, which is exactly 1.0531 on the y-axis. That's the y-intercept. This one here is the slope. Okay, so the gradient or the slope, and then we've got x and y. So, like I said, you could use this to predict. So, if we were to look at this axis here, and we were to say, okay, well, what if it was let's pick a number. What if it was, say, 4.5 on this axis? So here, 4.5. And again, I'm just going to do a really rough job. Whoops, that's terrible. But just do a really, really rough job and just kind of go here and then go all the way across, roughly, to here. And where it touches here is where we're predicting the y value. But you can do this you can do this graphically like I just did, but you can also use this formula. Like I chose 4.5, right? So let's figure this out. If we had, just write it over here. So y equals 1.5838 times the x value. The x value is 4.5 plus 1.0531. So I just wrote the calculation here. So if we know the x value here, this is the x value, this is b, and this is m, y equals mx plus b, or m times x plus b. Let's put this in a calculator and see what we get. Okay, so 1.5838 times 4.5 equals this number, plus 1.0531. And we get 8.1802. And if you look, this kind of lines up with what I did graphically, see? You bring that across, it crosses over just after 8, so the exact value is 8.1802. That's pretty cool that you can do this just in Excel. So you can plot all your data out, okay, just raw data like this, just raw data, and you can tell Excel to build a scatter plot, you can tell Excel to do a regression, and then you can now use that to predict some unknown y value from the known, from an x value that you've observed, and you can predict what that might be. So that means if someone comes in our organization, this looks like it's a job satisfaction survey for all our employees that work in different departments. So if we've got a brand new employee, and we know that employee has rated ideas as, say, 4.5, we can predict that their job satisfaction will be 8.18. Do you know what I mean? So just based upon this one, we can predict what their overall job satisfaction will be, this one. And we've done that by training the model on this data. And what you're doing right now is called machine learning. Regression is a very common machine learning model. And what we've just done is we've trained the model based upon this training data, okay? And then we're using it to predict something new. Pretty cool. And a very, very simple idea. Give me a thumbs up in the Zoom chat, please, if you're following along, and if I'm going too fast, just let me know. But please let me know if everything's okay so far, and we'll move on to the next ideas. Jesse, Janithi, Junyu, everyone good? Yep, excellent. All right, thanks for the feedback. Okay, so let's clear the ink out from here and go back to our slides. So we just looked at the what the meaning of the trend line tool is. It basically helps you build a regression, and by ticking these boxes, display equation on chart and display R squared value. The R squared value is useful because it tells you how good the model is. If this number is like 0.5 or below, throw the model out, it's no good. If this model is, between 0.5 and say 7, it's okay. If it's from 0.7 to 1, it's pretty good. And it's a good predictor. This one's pretty good. Okay, what's next? So all this math is just basically what I was saying over here. It's just y equals mx plus b is what we're saying here. So don't get confused by all these funny symbols and whatnot. It's basically just what I said before, y equals mx plus b. And they're throwing in this little term here at the end. This is just the error term. So all of this is saying what I just went through slowly with you. So we can use this formula to predict a y from a given value of x. All right, so let's talk about residuals. Now, like, how do you build this line in the first place? Like, how do you actually build this line? Well, what you're trying to do in actual fact is you're trying to minimize the error between 2 points. Let's just go to a blank slide for a second. Let's make this really simple. So here is just a simple scatter plot. And let's say we've got one data point, let's say here, and maybe one here, and maybe, I don't know, one here. And we're going to try and just draw a line of best fit. So what happens is, Excel will try and put a line in that minimizes the error between each of these data points. And what I mean is, if you measure this distance between this data point and let's get a different color. Let's use blue. Yeah, so if you measure this distance here, okay, this distance, whatever this is, let's call it D1, the distance 1, and then this distance here, this line should minimize the distances between the line and each data point. This is called the residual. This distance is called the residual. And I'll just do one more orange data point. Let's do one more that's like really far away. Let's do one over here. This one here. Yeah, it's a long, long, long way away. This would be like an outlier. Call this D4. So what we can do is we can take these distances. Let's just pretend that this is like distance 1. This is 1 unit. We measure this on, we measure this and subtract whatever this y value is, and that gives us the distance. Let's say it's 1. Let's say this is 4 here on the scale, and this is 3. 4 minus 3 is 1. So there's 1 unit. Let's pretend that this is 1 unit, and this is 1 unit as well. And this one here, let's just guess, let's say it's 7 units. Okay. What we do is we take each of these distances and we just square them. One squared plus 1 squared plus 1 squared is like 3, plus 7 squared. Now, the reason why we square it is to penalize or exaggerate the error or the residual for data points that are far, far away from the regression. And the reason why we do that, the squaring, is to give us a better overall sense for this overall number. Okay, this is the squared error. Squared error. And like the bigger this number is, that tells us that the line does a worse job at summarizing the data points. The lower this number is, the better this line summarizes all the data points. Like I said before, you know, when I had the love hearts here, like if we had all of the data points were on this line, the residuals would be 0 because they're right on the line. So the squared error would be 0. 0 squared plus 0 squared plus 0 squared plus 0 squared, whole thing would be 0. And that tells us that this line is a perfect fit with all the data points. And whoops, I just cleared it all, sorry. Didn't mean to clear it all. But when it's not 0, when it's high, that means that the line does a poor job at summarizing all the data points. Let's go back to our slide then. So that's just what this is saying. It's just saying that residuals are the observed errors associated with estimating the value of the dependent variable using the regression line, like how far away each data point is. The best fitting line minimizes the sum of the squares of the residuals, just like I said before. The sum of the squares, like 1 squared plus 1 squared plus 1 squared plus 7 squared, is the sum of the squares of the residuals. Remember, the word residual just means the distance. So I hope all that makes sense. And you can actually get Excel to do this for you. You can go to data analysis regression, and you can get Excel to analyze that for you. Let's do it on our existing data set here. So we just go to data analysis and regression. We put in our Y value. Let's say we're trying to predict. Remember, the Y value is the dependent variable. So let's say satisfaction is dependent upon, let's say, ideas. What their rating is for ideas. I am able to express ideas for improving my job is what this is rating in the survey. Okay, we included labels when I selected, and then we'll also do residuals. We'll do residual plots. We'll just do all these. Let's go nuts. Won't worry about that, so click OK. Okay, so we use this as a basis for discussion. Go back to here. So this is the output. So when you run that regression tool, you get this type of output here, and I just want to use this maybe as an example when we talk about what we're seeing. And there's an example here as well. Let's in this slide here, it's got house age, square feet, and market value. You know, I guess the bigger the house is, the more money you're going to get. And then the older the house is, maybe the less money? I don't know, because it's like run down and such. So anyway, there's possibly a relationship here, and this is built out on a scatter plot. Here we're just mapping out square feet along the x-axis. That's the independent variable, and then market value is the dependent variable. So market value depends on square feet, like the area. Bigger the house, the more money. So home value depends on the house. So we know that the independent variable is the square feet, and the dependent variable is the market value. Regression A is better than regression B because it minimizes the sum of the squares of the residuals. So you can see we've got 2 regressions, and we're going to choose A because it better fits the data. It minimizes the sum of the squares of the residuals. Squaring all the distances gives you a lower number when you use A than B. So A is the better regression. And just repeating this, you know, we square the residuals to penalize data points that are further away from the regression. Here is a trend line with, you know, our equation for the regression, and our R squared value. R squared value is okay, like it's pretty average, like it's not great, it's not terrible. So we could say that square feet is like a fairly weak indicator of market value. If this R squared value is closer to 1, that would be a better model. And then we've got all this output. Let's go through this output and we'll talk about how to interpret each of these things that we see in the output. See, we've got, I'll zoom in a bit. We've got multiple R, R squared, adjusted R squared, all this stuff. It's very confusing. Let's demystify it. Let's talk about multiple R. Multiple R is the sample correlation coefficient. So it's going to go from -1 to +1. When it's +1, you have a correlation that is a strong positive correlation. So it goes like this. And you've got your regression. This is going to be close to +1. When you've got a regression that, well, when you've got a multiple R value that is -1, it's going to look like this. This is going to be close to -1. -1 means it's sloping down, +1 means it's sloping up, which means that +1 means that as X increases, Y increases. As square feet increases, market price increases. This one means that as X increases, Y decreases. Okay. Okay, so that's that multiple R value. Now this multiple R value is 0.73, so this tells us that it's more like this. It's more like this. It's not as severe, like 0.73 might be a little bit flatter, if that makes sense. We'll do blue. So yeah, 0.73 might be a bit flatter. It might be more like this. Let's have a look at our multiple R value for our output. Multiple R is 0.84, so it's good. So it's a positive correlation. What about the next one? What is the R squared value? R squared, as we said before, is the square of the residuals. Coefficient of determinant varies from 0, no fit, to 1, perfect fit. So, I'm sorry, it's not the square of the residual. Sorry, R squared is just the coefficient of determinant. It's just when this is close to 1, that means that, as I said before, with all the love hearts on the line, if it was all the data points are on this line, that means it'll be 1, that the regression will be a perfect fit for the data. 0.53 means that the data points are a bit more scattered around the regression. They're not so much close to the regression. They're sort of scattered all over the place, but not too far away. 0 would mean that they're really scattered, that the line does a terrible job at summarizing the data. Let's see what our R squared value is for this. This is pretty good. 0.71, that means it's pretty good. Adjusted R squared. Adjusted R squared for sample size. So when you've got a low number of samples, this obviously means that you don't really have enough data to make an accurate model. Like imagine if we just had 3 data points, the regression would, even though the R squared value might be very high, you have to take into account that you've only got 3 samples. So adjusted R squared takes into account the sample size. So here it's just a little bit lower than R squared because there's a low number of samples. Let's see what it is for us. Yeah, so we don't have a lot of samples here. Let's count them. We've only got 33 down the bottom here, 33 samples. So that's not a big number. So you can see it's adjusted it down because we've got a low number of samples. And the standard error is the variability between the observed and predicted Y values. So we've got some training data here. Okay, and it's the variability between what we observed and what we predicted. And how do we actually read this? So we could say, let's just put this in English. Same slide, but just putting this into words. So with this R-squared value, we can say that 53% of the variation in home market values can be explained by home size. That's what this R-squared can be interpreted as. 53% of the variation can be explained by home size, by square feet. The standard error of $7,287 is less than the standard deviation of 10,553, which is not shown in this output, but that's the computed standard deviation. So moving on, interpreting the coefficients. So here we have in the output, we've got a bunch of coefficients, see here? So let's talk about what this means. When the house size increases by 1 unit, or one square foot, the value of the house increases by 35.036 units. So see that term there, that coefficient, 35.036. Over here, see that 35, see how it says square feet coefficient, 35.0363. So for every 1 unit of square feet, the house price shifts by 35.036 dollars. Let's look at ours. The coefficient for ideas is here. So for every 1 point for ideas in our survey, overall job satisfaction moves 1.583 points. So if you're an employer and these are your employees, you might want to focus heavily on ideas, because if you can make your employees feel like they're able to express their ideas for improving their job, then you're likely to increase their overall job satisfaction. For every 1 unit improvement for this, your employees score this area, job satisfaction goes up by 1.583. Pretty cool. So that's the coefficient, and so it's the same number here. Likewise, you'll see a coefficient here, 1.053. That's the same number that we're seeing here. This is the coefficient for the y-axis, the y-intercept. You can see here it says intercept, that's the y-intercept coefficient or number. Ideas is the gradient, this one here. Okay, what else? Estimating or predicting. So the estimated market value of a home with 2,200 square feet would be, and this is just y equals mx plus b. So just substituting for x, if you substitute 2,200 square feet, like right here, go zoop, and then zoop, you're going to get 109,752, which is right where my mouse is. We just can do that either graphically by just doing that, or doing it algorithmically by substituting 2,200 into this formula, running it through a calculator to get the predicted y, which comes out to be the same value. Okay, and confidence intervals. So where are we? Over here. See where it says lower 95%, upper 95%. Let's talk about how to interpret this part. Confidence intervals. So these provide information about the unknown values of the true regression coefficients, accounting for sampling error. So interpreting this, the home market value, for the home market value data, a 95% confidence interval for square feet variable is 24.49 to 45.48. So that means that the true parameter is, with a 95% confidence, is going to be between 24.49 and 45.48. And that's with a 95% confidence. Okay, and it goes on to say here that although we estimated that a house with 1,750 square feet has a market value of this just by substituting this into the x and running it through the same formula, If the true population parameters are at the extremes of the confidence intervals, the estimate might be as low as this and as high as this. So we can use this output to give us kind of like a range within which that true number might sit. So if you were using this, if you're a real estate agent, you're using this model to predict what the market value would be just by measuring the area of the house. You could say definitely that we think it's going to be $93,986 as the market value, but using this confidence interval here, you can say that it's going to be plus or minus. So it's the gradient could be as low as 24.59. So the coefficient here is 35, but it could be as low as 24 and it could be as high as 45. So by putting those two coefficients in, the lower bound and the upper bound, this will give you a better understanding of the range down here. Okay, so residual analysis. So the residual is just the actual y value minus the predicted y value, so just subtracting the two. The standardized residual is where you take that number that you just computed and you divide it by the standard deviation. And we can use this as a useful way to eliminate outliers from our model. So outliers are anything that are above or below plus or minus 3 standard residuals. This is how we can identify outliers. So let's talk about the residual output. Now I've got these down below. There's this big table with all of these numbers in here. Let's figure out what this means. We've got observation, predicted satisfaction, residuals, and standard residuals. I've also got these plots over here as well. We'll talk about this. Oops. So, and this is the second last slide. The first observation is that $90,000 is $90,000. So you can see here, observation 1, predicted market value is 96,159, and the actual is 90,000. So what is the difference between the two? So the actual was 90,000, but we predicted 96,159. So there is a difference, right? We were out by 6,159. Just subtract the actual minus the predicted. Actual minus predicted gives us this number here. As I said, outliers are anything with standard residuals plus or minus 3. So since this point has a standard residual of 4.53, we would consider this one as an outlier in our model. Let's have a look at our output down here. So if we look at this one here, observation number 1. So here we have the predicted satisfaction. Again, we're trying to predict their overall satisfaction, their job satisfaction, from what they rated as ideas. I'm able to express ideas for improving my job. So based upon this, if you went to say, hey, Sally, what would you rate out of 10 your ability to express ideas for improving your job? And Sally said, I think I rate that a 5 for this company. Then we can predict, hopefully, that her overall job satisfaction might be 9. So how close do we get for this first observation? We predicted 8.97 for Sally, which is pretty good. We're only out by 0.02. That's the residual. And the standard residual, remember, it's just the residual divided by the standard deviation, is this number. Now, if we look down this list, we're looking for any numbers that are above 3 or below -3. And so far, I don't see any. We don't have any. Cool. So we don't have any outliers, which is nice. So everyone's pretty much within there's no outliers is what we're trying to say. Okay, so that's basically how you can interpret this residual output. Pretty cool, right? So it's really nice to think that you can predict something and be able to look into a crystal ball and tell the future about something just based upon some simple analysis that we do in Excel. So we could predict fairly accurately what their overall satisfaction will be just from this one rating here. Okay, so that is the end of simple linear regression. So just to quickly summarize, simple linear regression allows you to take a data set like this, and it allows you to analyze the impact of one variable, one independent variable, and work out how that's going to impact a dependent variable. You can build a scatter plot just like this, and you can right click and go to add trend line, and then display equation on chart, this one here, like that, to get a model for predicting things. You can see how well that model predicts things by this R² value, and you can plug in x's to predict y's. In other words, you can plug in independent variables to predict what the dependent variable will be. Also, you can take this data set, you can run it through the data analysis tool and regression. Okay, this one here. You can run it through just like so. And you can use that to output a model again. So this you can build a model just from this. There are your coefficients. There's the y-intercept. That's your gradient. Then you just plug in your x and you can predict the y. These other numbers tell you how good the model is. Multiple R is useful for, as we said, for, look over here. So this tells you whether it's positive or negatively correlated and to what degree. R² tells you the fit of the regression with the data. Closer to 1 is good, closer to 0 is bad. Adjusted R² is like R², it takes into account the number of samples, and the standard error tells you the variability between the predicted and observed y values. We also spoke about what the coefficients mean. We spoke about how to use these lower and upper bound confidence levels. Just substitute the m for y equals mx plus b for your lower bound to get the lower estimate, and then substitute this value for m instead of this one to get the upper bound, and that's within a 95% confidence interval. And then we also finished off by talking about residual output. So we can see what the predicted was, subtract the actual from the predicted to get the residual, and divide the residual by the standard deviation to get the standard residual. And anything above or below +3 and -3 would indicate an outlier. So you might want to just maybe disregard that for your model and rebuild the model. So we'll finish off just by thinking about this last idea here, and then I'll mark the roll, which is multiple linear regression. And so let's have a quick look at this. This only goes for 5 minutes, then I'll mark the roll.
Fall in love with Hungry Jack's new Jack's Fried Chicken pieces. Crunchy.
StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. StatQuest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today we're going to be talking about multiple regression, and it's going to be
Clearly explained!
This StatQuest builds on the one for linear regression, so if you haven't already seen that one yet, check it out. Alright, now let's get to it. People who don't understand linear regression tend to make a big deal out of the differences between simple and multiple regression. It's not a big deal, and the StatQuest on simple linear regression already covered most of the concepts we're going to cover here. You might recall from the StatQuest on linear regression that simple regression is just fitting a line to data, We're interested in the R-squared and the p-value to evaluate how well that line fits the data. In that same StatQuest, I also showed you how to fit a plane to data. Well, that's what multiple regression is. You fit a plane or some higher dimensional object to your data. A term like higher dimensional object sounds really fancy and complicated, but it's not. All it means is that we're adding additional data to the model. In the previous example, all that meant was that instead of just modeling body length by mouse weight, we modeled body length using mouse weight and tail length. If we added additional factors like the amount of food eaten or the amount of time spent running on a wheel, well, those would be considered additional dimensions, but they're really just additional pieces of data that we can add to our fancy equation. So from the StatQuest on linear regression, you may remember the first thing we did was calculate R-squared. Well, the good news is calculating R-squared is the exact same for both simple regression and multiple regression. There's absolutely no difference. Here's the equation for R-squared, and we plug in the values for the sums of squares around the fit, and then we plug in the sums of squares around the mean value for the body length. Regardless of how much additional data we add to our fancy equation, if we're using it to predict body length, then we use the sums of squares around the body length.
So I'll just pause it there because I don't want to go into too much detail here. Just don't worry about the math. But what I will say about multiple regression is that with simple linear regression, we just have one independent variable, right? And one dependent variable. But with multiple linear regression, it's often the case in the real world that the dependent variable is affected by multiple factors. For example, your GPA is not just impacted by how many hours you study. That would be a very naive or simple, too simplistic approach to predict your GPA. We'd probably have to take into account, let's say, the level of difficulty of the courses that you're studying. Sure, we could take the number of hours that you study. We could also take the number of hours that you work, because the more tired and stressed you are, the better you're able to perform academically. We might also take into account your family situation. So if you're with family and have lots of family support, you're likely to do a lot better in your studies than if you don't. So what I'm trying to say is that your GPA might be dependent upon multiple factors. And that's what we use multiple linear regression for. It's where we think about how multiple factors impact our Y value. So it's more than one dimension. Here we've got body length of a mouse is determined by mouse weight and also the tail length. So we've got two independent variables that help you predict the body length. And that's where I want to leave that discussion, I think, for today. And we'll pick up on this next week. And multiple linear regression and simple linear regression are two things that you can use for the assignment to help you predict the customer spend based upon those other factors. Okay, let's get out of this, and I'll just put the attendance code up on the screen, and then you can mark yourself off for today. So guys, I just spent, I just wanted to go slow today and just make sure everyone's understanding each of those slides. And I hope that was useful for today. Here's the attendance code, and we'll definitely do some workshop stuff on the assignment tomorrow in our tutorial. Please have a read over the assignment, and then tomorrow we'll start to build out the report, okay? So let's see.